The intermediate system routing protocol for layer 3 engineers, I would like to call this as layer 3 engineer because you are of course above layer 3. So this is a high level review of the entire story, ISIS, followed by the loop free alternate, topology independent loop free alternate in segment routing with ISIS. So it's a big overall delivery, ISIS, segment routing, and the failover loop, which is nothing but the topology independent loop free alternate. And this is not Cisco, this is Juniper. Alright, so it's a link state routing protocol, as we know, and it is based on ISO, OSI CLNS. It's not based on IP. It's not an IP protocol, whereas OSPF is a IP layer protocol, network layer protocol. This one is older than OSPF, so it's ISO or OSI CLNS based protocol, meaning it fits in layer 2. If you see the last point, it directly runs over layer 2. So there is no IP dependency. MAC address only matters. For example, to decide a designated router, after the priority, it is the MAC address. The highest MAC address becomes the designated router. So that's one of the hint that it's a layer 2. It runs directly on layer 2. Highly scalable protocol, of course, it is highly scalable. Link state routing protocols and having multiple areas preferred in service provider network. And here we see type length value, means it's nothing but PDUs, the packets with various extensions that can support ISIS for various features, that can make the ISIS to support various features. Now, why it is fit for best for service provider? The TLV extensions. It has got flexible TLV extensions, IPv6, MPLS, segment routing. In all this, ISIS is easily fitting because the extensions are available for easy deployment. Anyhow, we are not going to do anything with the extension as we enable ISIS in this environment. Like a plug and play, the TLVs gets added and ISIS starts working in those environments. Convergence, stable convergence, large topology. You'll see why this is better for large topology than OSPF. We don't have ABR concept here. We don't have stub necessary. You don't need to configure stub here. So this supports a large topology actually. So it's used in the core like tier 1 ISPs, MPLS core, etc. The difference, as we already know, ISIS works directly on layer 2, OSPF is on layer 3. Scalability, highly scalable compared to OSPF. And design, flat design meaning single area, or try having L2. We have L1, L2. L1 is within an area, L2 is between areas. So recommended to have a flat single area in core ISP. Here that's what it means, core ISP. If you are using it, keep it as flat or If you have multiple areas, then make all the router L2, so that the VPN concepts, the segment routing, the loop-free alternate topology independent can work more effectively. You will have a clear distributed database. That's the reason why it's recommended to have flat or L2 level. OSPF, we have multiple areas with the ABRs. So ABR takes care of distribution of routes from one area to another, whereas in ISIS we don't have ABR. It is the L2 the one which makes one area to learn the routes of other area. No L1 routers will have routes of other area. They got only a default route given by L1, L2 routers. So while designing for core, it's recommended to have L2 or flat. Extension, TLV is easy, whereas OSPF you have complex LSA types. That's why I consider it as complex. Too many LSA types. We have come across type 4, type 5, type 7, even type 9 for segment routing, IPv6. We have those things in OSPF. Here we don't have too many LSA types. Instead we have TLVs. So TLVs are like attachable headers, extendable headers in ISIS header. Extendable fields in ISIS header. It's just get attached. When you are enabling ISIS for segment routing, you got the new field that carries segment router related database information, metric information. Similarly for IPv6, when you enable ISIS, whatever the necessary fields that are needed, that gets attached. Kind of extendable header ISIS has got.
I see.
Yeah, in OSPF, if you remember, we have layer 3, and you have the area ID, the router ID, the authentication type, the message type. That's the very first field. Those are fixed fields, and at last you have authentication type and authentication string. That's it. It's fixed. So the complexity increases. You need to now have different type of LSAs now in OSPF, because different type of LSA is needed to carry different type of advertisement. Whereas here it is simply TLVs, plug and play, fields getting added and removed depending on the environment where it is in. When we see the packet capture, we'll get more picture. We'll get more better light on it. Yeah. So when we do the lab, I'll capture the packets for ISIS as well as segment routing, as well as the topology independent loop-free alternate packets, the rerouting, all the stuff. Then you will get better idea of this TLV. When you see the packet, the header, how it changes according to the environment, you will get a better idea.
Thank you.
So we know this ISIS have got this two hierarchy design. Level 1 is within the area intra, level 2 is between area inter. So all the backbone routers need to be L1, L2, so that it can have both routes of local area as well as the other area routes. L2 is like a backbone in OSPF area 0. packet types, we have intermediate system to intermediate system hello, IIH. We have LSP, which is P packet data unit, protocol data unit, PDU. LSP is link state protocol data unit. It's equal to packet. That's why I use the word packet in the beginning. Packets. You can call it as link state packets, LSP. Easy to understand than protocol data unit. It's nothing but packets. And then we have two different sequence number here. Complete sequence number, PDU, packet, or partial sequence number, PDU. So depending on the type of advertisement, if you are going to fully advertise the whole database to someone, then it is going to be CSNP, number getting incremented. If it is partial, only the change, then it is going to be PSNP, number getting incremented. Now these packet types, why do we need the hello packets? They are needed for neighbor discovery, and the other three are needed for database synchronization. Adjacency. Sorry, I didn't ask you. So adjacencies, the hello packets are exchanged same like what other protocols discover by sending hello packet. ISIS also does the same thing. And very important here is the system ID. We don't have any layer 3 kind of identification like router ID with 32-bit. Here we got a system ID validation. In the network entity title, we have system ID after area ID. So it is the system ID that is validated. The system ID need to be same if it is L1 adjacency. The system ID, I am very sorry. System ID should be unique whether it is L1 or L2. The system ID need to be unique. It's equal to router ID. System ID need to be unique for every device, whether it is L1 or L2. So hello packets are exchanged with the system ID info. That's how one router learns about the other router. It's the system ID that helps to identify a device, and it need to be unique. Whether it is L1 or L2 doesn't matter, it need to be unique. Next is the level matching. Same area, level 1 need to be matched. Different area, it's L2. L2, different area, L1, same area adjacency. So if these two routers are same area, then need to be L1. That's how they form adjacency, L1 adjacency, by comparing the area ID that is coming in the hello exchange. If it is coming from different area, then it need to be L2, and L2 adjacency get formed. So same level is needed to form neighbor if the area is same. I think I'm confusing here. Same area, L1 adjacency. It needs to match L1. If the level is L2 on both sides, then it's different area. That's what here exactly I should say. Different area, L2 adjacency, same area, L1 adjacency. So here it is saying matching area, meaning for L1. Simple.
Yeah, makes sense.
Network entity title. This is something very important for ISIS. The reason is this has got three main things. One is the area, the other one is the system, and then end selector. Now, the size can be somewhere between 13 byte to 20 byte. The whole size can be anywhere between 13 to 20. Now, 1 minute. This will be always 0 end selector when we are having the CLNS ISO version of ISIS. And then this is the system ID. This is 1 byte. This is 6 byte. System ID 6 byte. So totally 7 byte is covered, and remaining are area ID. So if you see, area ID can be anywhere between 13 to 20 byte, meaning this can go up to 20 byte size. Totally 20 bytes. So this is like we already consumed 6 plus 1 7, so you got 13 to 20 byte. That's what I mean, 13 to 20 byte. Area ID can be 13 to 20 byte size, and how much you see here is 1 2 and 3. Only 3 byte as of now we have. This is the minimum. You can go up to 20 byte. Now what is this 49 AFI? This is to say that this ISIS is working privately. According to me, other than this 49, no other numbers we use today, but there are some numbers like 46 available for some purpose, but no one is using that. 49, we always use 49. But before I go to that AFI, let's finish this in a. Let's repeat once and understand, and then we'll go there. Now this portion, the system ID, people sometimes take MAC address and use it because this is 1 to 6 bytes. MAC address is also 6 byte, 48 bit. Sometimes people take the IPv4 address and add some number in between, and they make it as 6 byte, 48 bit. So depending on your comfort, like if you're going to copy the MAC address and put it here, MAC address of any interface, need not to be Lubeck interface or a physical interface, the first interface, it can be any MAC address, just enough. You need a 6 byte, and that 6 byte need to be unique for each device. So that's what we need to make sure that it is unique. And this is area 1, and it's a private area, 49, area 1. We can go up to 20 byte in total size. Right now we have 6 plus 1 7, 8 9 10 bytes covered. So you got another 10 bytes just for area. Now about AFI, authority and format identifier. Authority and format identifier, AFI. In the net address, or it's the first field in the NSAP, which is also called as net address, NSAP address. defines the address authority, meaning whether it is private or public, defines the address format used in OSI based addressing CLNS. Yes, it's the CLNS OSI based addressing format. Now, why we need this AFI? Designed for OSI networks, used in NSAP format, network service access point, means net ID. So this is not seen in any other routing protocols because we are not using any NSAP address other than ISIS. We have only IP or TCP based protocol. This is the only one which is NSAP or CLNS based, OSI network based. So what it is helping us, it helps to identify who assigned this address, meaning who in the sense, is it public or private, is it ISP or the enterprises, and what format it follows. So when you say 49, you understand that it is OSI network format or NSAP format. So where it is located, it is right in the beginning. It's always the first byte. Like N selector is always the last byte. N selector is always 00, last byte. Likewise, this is always 49, first byte. AFI is first byte. Now what does that AFI 49 means? It means that it's a private address, and this is locally administered address, and service provider networks also use in as an IGP protocol. They use it within the autonomous system. This is highly scalable protocol. So enterprises people also use it with the same 49. But because it's an IGP protocol, never mind if both uses 49, that's not a problem. They are not going to advertise it outside the autonomous system using ISIS. They're not going to form neighborship outside the autonomous system using ISIS. So whether it is service provider or enterprises, they put only 49. Why AF49 is used everywhere? Because AF49 is private, there is no need for global registration. And it's flexible address design, simple and consistent. So almost all ISIS deployment will use 49. That's simple. This is one thing which not many people are focusing on, which is always being confusion for the learners. So I thought I should keep some slides for AF49. We have it here. See, the other AFI values are 47, but no one uses the pub. It's like if you are going to use ISIS in the place of BGP, you may need this. And then 39 iOS CD, ICD, rarely used in the modern networks. I have never seen. There is no connection between this ID and routing. It is simply to say whether it is global or local. That's it. So no impact in the routing decision. AFI has got no impact. No effect in shortest path first calculation. Area ID matters in SPF, but not the AFI. So it is just used for address format identification, and there is no connection. There is ISIS don't depend on AFI value at all. It's just a label to say this is a private ISIS address, nothing more. Now we don't have backup designated router concept in ISIS. We got only DIS. IS stands for router here. Instead of saying router, we say intermediate system. So DIS is designated intermediate system. Only one designated router, not two. In OSPF we have two. Backup designated router and designated router. And the big difference is this convergence. When a DR goes down in OSPF, BDR becomes a DR. We don't have BDR here. Then how this is fast in convergence? Now, the preemption story, if you remember in OSPF, the preemption story is a opposite story here. There in OSPF, the one with the higher priority comes after the election. After the election, if you make a router, if you configure a router with a high priority, is of no use. Once the election is over, need to wait for another election to become DR, because it's non-preemptive. Even though the priority that you set may be the highest, but still the DR is already there, elected. So this new one which you are trying to make it as DR will not take position immediately. It needs to undergo a re-election. For that you need to kill the OSPF process and reinitiate, meaning you need to refresh OSPF. That story is not here. This is preemptive. So if any device comes with better priority or a bigger MAC address, wins the election. Yeah. So convergence happens faster. When one disk goes down, immediately other disk takes the position. Preemption is there. Designated intermediate system is like DR in OSPF, and this is seen in broadcast environment, the Ethernet wires. Yeah, this is not for the whole area, it is for the LAN. In a LAN environment, when we have more than two routers participating in election, then there is need for a leader, there is need for a disk. That's where this comes into picture. Next, how is the disk elected? As I said, high priority. And then if the priority is same, then it is high MAC address. Alright, metric in ISIS. We have two types of metric, the narrow metric and the wide metric. The narrow metric is 6-bit only. So 2 to the power of 6, only that much you can have as a metric. In a very small environment, that is okay. But ISIS is mostly used in the place where we have traffic engineering, segment routing, so it is always good to go with wide metric. When we configure ISIS without fail, put wide metric so that we can have traffic engineering, segment routing, etc. Alright, now something related to Junos, ISIS architecture. ISIS runs under the protocol mode ISIS. Same like Cisco, this is activated under interface. There is no network command in OSPF as well as, in Cisco as well as ISIS. We don't have that option, network statement option. In Cisco we have OSPF in two ways, interface based and network based. We don't have such thing for ISIS both in Cisco as well as Juniper. It's only interface based activation. When you see a sample configuration, it will be easy. Here it is. First thing, we globally configure the router ID. This is not just only for ISIS. This is common for all routing protocol. Set routing option router ID. Followed by set protocol. ISIS, meaning if you want only level 2, then you can say this. Level 1 disable. So indirectly we are saying I don't want L1. Sorry, here directly we are saying I don't want L1, which means I want only L2. That's what indirectly conveyed. And then we are going to say what all interfaces will be running ISIS. And why we say passive, because it's a loopback interface. We don't form any adjacency in that interface. Only the network of that loopback interface should be advertised. We are not going to send any hello packet. We are not trying to form any neighbor. Not possible because it's loopback interface. So it is always a good practice to say this passive word for loopback interface. Set protocol ISIS interface loopback 0 passive. And here we also see that ISIS is running on gig 000.0. Here it is always like unit .0.1. That's how we use the interface in Juniper. In Juniper we always put unit number to the interface. We don't straight away use the interface. We go with the unit, and we can define different type, IPv4 type, IPv6 type for different unit. I like this portion of Juniper a lot. Take one physical interface, create multiple type of the same interface, and differentiation is given through that unit number. More we'll see in the command line. This is a mandatory configuration. This need to be unique. Every router, whether it is different area or same area, we need to make sure that this, especially this portion, is unique. When this is unique, definitely the whole address is going to be unique. So, thanks. So this is just the configuration part of ISIS. This slide and the previous slide, and now how do we enable ISIS? It's per interface. So you can say like this: I want only L2 on this interface, and then it needs to be a point-to-point. So that there won't be a disselection on that link. If you are sure that there is only two router, you can very well go with point to point. So as I said, passive interface is the one which never advertises, which never sends hello packet, which never try to form any adjacency, and it is only the network that is advertised. the network on the loopback interface is advertised, but there is no hello packet sent over the interface. No adjacency can be formed in loopback, so we have to put passive. Wide metric configuration. Why do we need this? Because it's only 6-bit for narrow metric, which is not sufficient for a large environment. 2 to the power of 6 is the maximum size of a metric if you leave it default, which is very small number. Same case with Cisco. So we always say wide metric for traffic engineering, for segment routing, for IPv6 related ISS. So make it as a practice to say wide metric always, whether it is small or big, doesn't matter. Are you configuring ISIS? Then put this command: set protocol ISIS wide metric only. Simple. Problem solved. Later you will not face any issues. This matters a lot in traffic engineering environment. So if you miss to put in one device, then there will be a problem in forming adjacency. The metric style should match to form adjacency. Now to enable authentication, this is the procedure. This is the global level for all the interfaces that runs ISIS. If you wish to have same pre-shared key, then you say set protocol ISIS authentication type and then the key. Now I don't want an all interface, just want on one interface, then go with this one. Set protocol ISIS and then the interface name and then the authentication type MD5, and next line set protocol ISIS interface and then authentication key and then Juniper 123. So per interface, this is the syntax. Global, this is the syntax. Some verification commands: show ISIS adjacency, show ISIS database, show ISIS interface, show route protocol ISIS. We have done this many times in various protocols in Cisco. Similar show commands. Instead of saying neighbor, we say adjacency. This command is same in Cisco. Same in Cisco. Slight difference, we used to say show IP route or show IPv4 route and iOS XR in Cisco. In Juniper it is show route simply. Show route protocol ISIS. It can filter out only ISIS route and show you only the ISIS route. Troubleshooting, if there is any issue, first check the adjacency by typing this command: show ISIS adjacency. What may be the problem stopping you forming adjacency? The net ID mismatch. Maybe the area ID is different, but the type is L1. If the area ID is different, you need to have type L2. So that mismatch. MTU mismatch also matters. And then the authentication. These are all the small mistakes that someone can do. ISIS with MPLS, used as IGP protocol for MPLS core and carries loopback reachability, so that you can form a VPN. Alright, so when you are using ISIS, you need to enable LDP for label distribution. It's not like Cisco, we have to enable it separately. LDP need to be enabled. RSVP tree or segment routing. Today we'll focus on segment routing, then this other two. The best practices. Use L2 only in service provider core. As I said earlier, you can have any number of areas, no problem, but make sure you put L2 everywhere so that the database distribution will be there with all the routers, and all the routers will have common map. So if you're going to have a flat area or single area, then this is not a point for us. But when we have multiple areas in service provider core, because they have VPNs, the database need to have information about every single area, at least the loopback of other area. For that, we used to league route from L2 to L1 if it is not a flat network. We need to league route from L2 to L1, which is unnecessary. Simple, make it as L2 only everywhere, then all the routes will be available in every router. Then there won't be a problem for the traffic engineering to use. The traffic engineering needs to have the visibility to every single link. For that, we need to have L2 or single area that solves the problem. So that's the best practice for service provider core. Make it as L2 everywhere. And then use the loopback interface as a router ID. Yes, of course, we must use loopback interface as a router ID. We have seen in Cisco when we were doing layer 3 VPN. Same follows here. Juniper. Enable wide metric and use point to point wherever is possible. We saw in the sample configuration in previous page, we were saying gig 0/0/0.0 point to point. So that avoids unnecessary deselection in every link. Next is simple topology is good. Scaling ISIS supports large LSP labeled switch. Supports large link state protocol data unit or PDU database. Fast in convergence, hierarchy design we have. So it's very good, suitable protocol for leaf and spine architecture. Now, some advanced features like traffic engineering, ISIS with traffic engineering, segment routing MPLS, fast rerouting, topology dependent loop free alternate, and multi topology ISIS. Having having IPv6 and IPv4 together, multi topology ISIS. So these are all the advanced features that we have in ISIS. Now, here is the full configuration of what we have discussed so far. This is how we set router ID. This is how we configure net ID. And this is how we enable only L2, because we disable L1. Wide metric, running ISIS under the interfaces, and when you say on loopback, it need to be passive. And here also we again emphasize that it need to be L2. power interface level. And this is how we configure authentication globally for all ISIS running interface on this device. Alright, so we have seen the whole story of ISIS theoretically. It is a scalable protocol, flexible IGP protocol, and it is the recommended one for service provider. Service configurations are interface based, and it's a very good protocol for MPLS, segment routing, etc. We have just seen only the protocol ISIS. Now what we are going to see is the advanced topic in ISIS, meaning the loop-free topology independent alternate. For that we need to have an understanding of segment routing, so we'll also talk about segment routing now, and then we'll get into that. So far, is there any question, brother? Is everything good?
Everything's really good. No questions.
Thank you. Now, the advanced ISIS topology independent loop-free alternate and segment routing with ISIS, which is SRMPLS. Yes, the segment routing is of two different type. One is SRv6, which doesn't need an MPLS. This is SRMPLS. ISIS with SRMPLS. Why do we need this advanced feature? The time taken for the convergence, we want this to be less than 50 milliseconds. So when we don't have this loop-free alternate, topology independent loop-free alternate, the time taken is somewhere close to 200 milliseconds to 1 second, which is not an acceptable delay in service provider environment. 200 milliseconds to 1 second is not an acceptable delay in a service provider environment. It is seen as slow convergence. When the primary goes down to pick up the backup path from the database, it takes close to 1 second, which is not an acceptable delay. We need sub 50 millisecond protection. And we expect, a stable deterministic forwarding, scalable traffic engineering. So for this, the best solution is go with traffic engineering loop-free alternate, which is nothing but the fast convergence rerouting, which can guarantee you that 50 millisecond protection when we use with segment routing. So we have the base IGB protocol ISIS, and we got segment routing with MPLS, on which we have also enabled TI LFA. Then you can have that guaranteed 50 millisecond protection. So what is TI LFA? Topology independent loop-free alternate. It's nothing but fast rerouting. Without segment routing, when we do MPLS traffic engineering with RSVP, we used to do this one in a very difficult way. I hate that fast rerouting in MPLS RSVP traffic engineering. Because you need to go to each node and say, if this fails, take this. Not that easy, it's painful one. We do not know which node will fail which at what time. So we need to assume things, and we need to do fast rerouting configuration in various routers. But here we don't have such difficult approach. It's easy here. Simple commands you need to say. If link fails, if node fails, do this. Boom. That easy it is. I'm going to show you those configuration example in coming slides. It is there. So with topology independent loop free alternate, we have fast rerouting for the link as well as node failure. We need to define when the fast rerouting should happen. If node fails, should I do? Yes. Should I do if a link fails in that node? Yeah. So you have an option to mention those things. Alright, so the key concept is pre-computed backup path using segment routing. That's the secret of fast rerouting. So when it selects the path in the beginning itself, the backup path is also selected. Yeah, so not the primary path alone, the backup path is also selected. So that when the primary path goes down, you no need to do recalculation. It has already got the pre-computed backup path. It can easily jump to the backup path. These are all the different alternate, loop-free alternate methods, in which the best one is TI LFA. This is the best. Fast rerouting mechanism in ISIS and IGP, loop-free alternate, remote loop-free alternate, and then topology independent loop-free alternate. See the difference. Loop-free alternate, partial coverage, whereas topology independent is full coverage. This is the remote loop-free alternate. It's said as high coverage. Complexity, medium complexity. This is low, medium. Now convergence, super fast, ultra fast. That's why we go with this. We need segment routing for this, yes. Without segment routing, it is not possible to have topology independent loop-free alternate. Okay, so the working principle, it uses the SPF provided tree, the path, the shortest path tree. Post-convergence backup path. So it pre-computes the backup path so that it can use whenever the problem happens. So it pre-computes the backup path with the next hop so that when the primary fails, it can immediately swap to the backup path with the next hop, and it also installs the backup path in fib table, keeping it ready so that on failure it can instantly switch to the backup path. Very important, when the fib table is ready with the backup path, what else you need? That is the one which moves the packet. So everything is ready. Pre-computed backup path with next hop so that when the primary goes down post the convergence, it can use the backup path as primary. Topology independent loop-free alternate protection types. Using this, we can protect the link protection, meaning if link fails also we can take a decision. If node fails also we can take a decision. And then segment routing, LG protection.
No problem. Thank you.
Welcome. So it works for IPv4, IPv6, and MPLS. This protection here. TI LFA in ISIS. See, segment routing that depends on the link state routing protocols database, link state database. So ISIS provides that to segment routing. Now segment routing starts giving labels for each node, each prefix. See, there's a big difference in Cisco and ISIS in Juniper. In Cisco, node and link we don't differentiate. Means prefix segment ID and node segment ID. There is no difference there. We go to the loopback interface on Cisco device and we enable prefix sig ID. And we call that as node sig ID also, because we don't have sig ID for every single prefix. We just go with only one prefix, loopback interface prefix. So we use the same as a node sig ID in ISIS Cisco. That's not the case here. We have prefix sig ID as well as node sig ID separately. Anyway, that's not mentioned here. I'm just telling because we are from Cisco background. We were using only one sig ID per node, but we were doing that under the loopback interface, so that is also seen as a prefix sig ID in Cisco. That's not the case here. When we do the configuration, or when you see the sample configuration in today's class, after a few pages you will understand what I'm trying to say. Anyway, so we are here seeing that ISIS provides the picture of the topology itself. Service provider provides the label for the topology, means the prefixes and the nodes, and then these are now used by TI LFA. So we have ISIS and we have segment routing. Together it can provide a fast convergence. Come on, along with that, what is needed? Fast readout configuration is also needed. Okay, this is a sample configuration for topology independent loop free alternate. Set protocol ISIS, this interface L2, this is to enable ISIS, and this is the command that enables fast readout. Set protocol ISIS fast readout per prefix. It's not per node, it's per prefix. Topology independent loop free alternate. That easy, simple. This enables the router to calculate, pre-compute an alternate path for each prefix and keep it ready in the fib table, so that if something goes wrong, it can immediately swap the traffic to a new next hop. Set protocol ISIS fast readout per prefix, topology independent loop free alternate. Advantage of topology independent loop free alternate configuration, advanced advanced. What is that? You can say per prefix. You can also say node link protection. Link plus node can be set together. So set protocol ISIS fast readout per prefix, topology independent loop free alternate. This is where we stopped in the previous page. Now you're adding additionally node link protection. So if any one of this fails, then it's going to swap to a new path. This is only node. Set protocol ISIS fast reroute per prefix topology independent loop free alternate node protection. Just the node alone. This is node and link both together. According to my knowledge, this is what we have in Cisco. This is the only thing. For us, node, link, all same there. That's why we went under the loopback interface only to configure the SIG ID. Right, some verification command: show ISIS route extensive, which will show us even the labels, routing table, backup. Alright, so what do we need to see is in this, you need to look for the backup next hop and the stack of label for the alternate path. In lab, it will be more interesting when you see these things. So we are enabling the topology independent loop free alternate. So when you put these commands, you will be able to see the primary route, the backup route, and the label stack for the backup route, and also the backup next hop. That's really interesting to see. So if you want this, you need segment routing. If you want this topology independent loop free alternate advantage, the convergence which will take less than 50 milliseconds, then you need segment routing. What is the difference between layer 3 MPLS VPN and layer 3 MPLS traffic engineering and the segment routing? This is source based routing. Why we call it a source based routing? The head end router adds the label stack which is needed for packet switching or the label switching to reach the destination. So all the instructions that are necessary to move the packet from one end of the autonomous system to the other end is inserted right in the source router, the router where the SR begins. It's not every hop deciding what label to use, it's the source that decides. Source puts all the necessary instructions that is needed for the packet to flow through a particular path. Source based routing. No per flow state in the core. It's a source that determines, and based on the instruction in the source given by the source to the packets are going to flow. So here the packet carries the instructions, information, which are nothing but the list of segments. Here we don't call it as label, we call it as SIG ID, segments. It's actually MPLS label. Still this uses MPLS header, same 20-bit label. Only the difference is the segment routing global block is reserved 16,000 to 24,999, totally 8,000 labels. Okay, now different types of segment IDs. Node segment ID, which represents the router. Prefix segment ID, which represents a network, a prefix, a destination, a network. Adjacency SIG ID is just focusing only on the link that connects to the neighbor router. 1 minute. Okay. So we see these three type of IDs. One is to identify the device, the router itself. A unique ID is given. Unique label is given to identify the router itself. And then unique ID is given to each network. And then a unique ID is given for the link that connects to the neighbor. Link is identified, device is identified, and the networks on every device is also identified. For this only we have the global block reservation from 16,999 to 16,000 to 24,999. This one is from 25,000. And above. So there is no reservation for this. For this it will always use the range starting from 25,000. But for this we have a global block reservation. More is coming later. So we have three different segment types: adjacency segment, prefix segment, and router segment. And they all use the 20-bit MPLS label. Now, why do we need segment routing for this? So you no need to depend on that LDP and RSVP, which is adding too much complexity. We make use of that same IGP protocol that we already have. We definitely need an IGP protocol, so we already have it. When I have segment routing for traffic engineering, I can make use of that IGP, that ISIS. That's the biggest advantage. That's the big point here. No LDP, no RSVP. But still you can have better traffic engineering. That's the biggest advantage. Better traffic engineering, fast rerouting without these two. Simplified MPLS. Not multiple stacks of MPLS, simplified MPLS. Not transport label, service label, RSVP label. No such complexity on MPLS, simplified MPLS. So this of course contributes in better scalability, because when you reduce complexity, scalability improves. And the traffic engineering is native traffic engineering, meaning you don't depend on another protocol like RSVP, you just make use of the same local native ISIS, native traffic engineering. Now, segment routing plus ISIS integration. ISIS is the one which is going to provide the database for the segment routing to use, to which the SIG IDs are assigned or labels are assigned. Not only that, the distribution of the label is also carried out by ISIS. So ISIS has got the TLVs. ISIS has got that extension capability, the plug and play. So using that extended field, the SIG ID values are distributed. See, when the prefix reachability is distributed, which is nothing but the database, ISIS database, along with that, the SIG ID value is also distributed. The route information, the database is provided by ISIS. So the control plane that is steering the traffic is ISIS. The one which is pushing the traffic is based on the MPLS label. So data plane is MPLS. Data plane is MPLS. Though we say segment routing, it is basically MPLS label which is used in segment routing. But a reserved block, global block, as I said, 16,424.99. It's again MPLS only, though it is segment routing. We cannot say data plane as segment routing. Depends on MPLS, but not on LDP, not on RSVP. It's only the header we use. In IPv4, we have no other option. IPv4 header is fixed. You cannot extend it. That's why we put another layer, 2.5, called MPLS header, MPLS layer. So it is the MPLS layer, MPLS label used. The data plane is MPLS, control plane is ISIS. ISIS is the one which provides reachability to the prefixes, the database. Okay, so the flow is this: ISIS advertises the SIG ID for each node and prefixes. And now those SIG IDs are installed to the router. Now packets are going to be forwarded according to the label stack which is given by the head-end router, the source router. Are there any questions so far?
No questions so far.
So this is the basic configuration for MPLS. You see, we say set protocol MPLS on this interface, and then ISIS only with level 2, which we have seen earlier, same command. And this is the segment routing command: set protocol ISIS source packet routing MPLS. This is the command that enables segment routing. Set protocol ISIS. Easy, in Cisco we used to go under ISIS, and we used to say, I want segment routing and I want the loopback interface to be the router, all those difficult stuff. Here it is straightforward. Set protocol ISIS source packet routing MPLS. And this is how we set the SIG ID for a node. Set protocol ISIS source packet routing means we are enabling segment routing. Node segment IPv4 index 1001. What does that mean? It means 17,001 as a label. Why? Same as you learn in Cisco. Whatever you give as an index value, that gets added to the 16,000. 16,000 is the beginning of the segment routing global block, and this is the ending of the global block. So always it begins with 16,000 plus the index value that you put. That makes seg ID or node ID, node seg ID, node segment ID or label. So this is node seg ID. Set protocol ISIS source packet routing, node segment for IPv4, and then we say index value. This is prefix. Set protocol ISIS. See, first the interface is loopback, the prefix on the loopback. So loopback is running ISIS. Now we say ISIS source packet routing. Source packet routing is nothing but segment routing. That's what we learned. Source based. Source packet routing. Prefix segment. See the word node segment here. And this is prefix segment. This is not seen in Cisco. In Cisco we do only under the loopback interface. And we call that as node segment as well as prefix segment. Here we have a separate index for node and a separate index for prefix. So now this becomes 16,000 plus 2001, which is 18,001. 18,001 is the prefix SIG ID, 17,001 is the node SIG ID we configured. Segment routing global block. As I said, this is the global block, but you can also set different blocks by using this command: set protocol ISIS source packet routing, which is nothing but segment routing, sRGB global block, starting label, and the range. But this is default. Even if you don't configure, this is what you will have. Then why I need this? I need this syntax so that I can have different block size if I want, but not recommended. Not recommended. Leave it default. Some verification: show ISIS database extensive. This is the new command which we have not seen in the previous pages. Show MPLS LSP label switch path. Show route forwarding table. So what do we see here? We are going to see the labels that will be used, and we'll also have that SIG ID mappings. Alright. So topology independent loop free alternate plus segment routing integration. It is for the fast reroute. For the backup path, pre-computed backup path. SR label stack for backup path. Advantages: you have the fast convergence, less than 50 millisecond protection. 50 millisecond protection. Alright, so for example, a link fails, immediately it triggers the TI LFA. Now the packets are encapsulated with a new set of labels, and it is going to now go through the alternate path, and no packet loss most of the time, because less than 50 milliseconds it takes to swap. SR reduces that LDP state, RSVP tunnel, you don't need all those things. And the convergence time also is reduced, improved fast convergence. For a large service provider backbone and for a data center fabric like leaf and spine design, this is a suitable one. Topology independent loop-free alternate. Right. So we will start from here in our next class. I'll stop.